Well, thank you first for staying this long. I really appreciate it that there are some people here. So my talk is about abstraction refinement, and I want to give you a quick overview of the talk. I will start with introducing the cigar algorithm. Then I will show you how it compares to similar approaches, and then briefly talk about ongoing research on this topic. Okay, let's start with the algorithm. So the background here is classical planning, and in particular we want to find optimal plans. So let's consider this easy example from the logistics domain where there's only a single truck, a single package, and we want to transport the package from location A to location B, so in one of these two states here. We have the actions that drive the truck from location A to location B here, and then we have load and unload, and the same actions in the location B. So, as you all know, this can be easily solved with Dijkstra, for example, and we can easily find an optimal plan here, which is to load the package in A, drive to B, and unload in B, of course. But this does not scale because of the state explosion problem, so we have to come up with tricks to find a good solution, or the optimal solution in our case. And we use abstractions here, so the overall goal is to find a good abstraction that will lead us towards the goal during the search. And we do that by starting with the coarsest abstraction that we can find, namely we abstract all the concrete states into a single abstract state. Now we only have a single state, which is the initial state and the goal state, because there is only one state, and all the actions just take us into the state again. And then iteratively we find a solution in the abstract state space and check where it fails in the concrete state space, and then refine the abstraction in such a way that it does not, that the same flaw cannot happen in the next iteration again. So the optimal plan here is doing nothing because we are already in the abstract goal state. But this, of course, does not satisfy the goal in the concrete state space because the package is not in room B if we do nothing. So we at least have to distinguish between is the package in location B or is it not. And we do this by splitting this state into two states, and then we update all the transitions. And this is our new current abstraction, and then we iterate again. We find an optimal solution in this abstraction, which would now be to unload the package in B. And as you all know, this does not work in the concrete state space because the preconditions of this operator are not met in the initial state. So both the package is not in the truck and the truck is not in location B. So we have two flaws that we can potentially use and split this state upon. And it doesn't matter which one we use. We could either split by the package or by the truck. And let's consider that we use the truck, the package again. So we split this state into two states, and we get this abstraction here. And we continue this process until we run out of time or memory. And then we calculate all the abstract goal distances, 2, 1, and 0. And we use this heuristic during search. Okay, so you might be interested in the relation to other classes of abstractions. For example, how does it compare to pattern databases? And an interesting observation is that our class of Cartesian abstractions is more general than pattern databases, but less general than merchant trunk abstractions. And we will see here why. As you might have noticed, the last abstraction that we yielded is just a pattern database, namely a projection to the package. We could also split this concrete state space in this way, then we would have two states, this one and this one. This would be a projection to the truck, or we can do both, and just this would, in this example, yield the complete state space. So But what cannot be done in pattern databases is splitting only a subset of the states. So this split here can be done in Cartesian abstractions, but it cannot be done in pattern databases. Okay, so one class of abstractions that is even more general is merchant shrink abstractions, where you could also combine this state with these two states. But this is not possible in Cartesian abstractions. Here we can only allow splits either horizontal or vertically. Okay. So why didn't we use any of the other already known formalisms? Pattern databases cannot be used for counterexample-guided abstraction refinement because each refinement at least doubles the number of abstract states, because each variable has at least two values, so we get a huge number of states with each refinement. On the other hand, Cartesian abstractions allow for a very fine-grained refinement. We can have the concrete state space and have just a single abstract state for half of it and very many abstract states for the other half, maybe because we are only interested in the other half. And merchant shrink abstractions cannot be used for this process because we cannot efficiently compute the concrete states an abstract state corresponds to. And we need this for updating the transitions between the abstract states. Okay, let's see how it compares to other approaches in the literature. For this, we set up an experiment of 30 minutes and 2 gigabytes of memory, the usual IPC setup. And for the cigar abstractions, we used 50 minutes of refinement and then 50 minutes of search. And we compare our method to 3 different abstraction-based heuristics, which is the IPDB heuristic, which is an efficient implementation of the pattern database heuristic with Patek-Hasselum's and others generation method. And then we have the 2 merchant shrink configurations that are part of the Stone Soup portfolio that won the last IPC competition. So, and then we have our method, and for comparison we list the blind heuristic, which is an uninformed heuristic. And when we look at the number of solved tasks across all the benchmark suite, we see that our method solves more problems than the first merchant shrink method, but is worse than the IPDB and the second merchant shrink heuristic. But what is interesting to note is when we look at the number of solved tasks that are solved by the blind heuristic, but not by an informed heuristic. For IPDB, this happens 30 times, and for the merchant shrink heuristic, 68 and 40 times, while we only fail to solve one problem that is solved by the blind heuristic. So we can say that the results, or our heuristic, is more robust than the other approaches because we can only improve on the blind heuristic. When we look at some example domains, we can see that it is usually the case that we perform better than 1 or 2 of the other approaches, usually not better than all 3. But in some domains, if, for example, in M' and mystery, we perform better than all 3 methods we compared against. Okay. And this can be partly explained when we look at the informedness of the heuristic. Here we have a plot of the estimate for the initial state for 3 different heuristics. The top one is the perfect heuristic. Then we have the cigar heuristic here, and we have the IPDB heuristic here. And they are all plotted against a growing abstraction. So this is the number of abstract states on a log scale. And as you can see, the cigar heuristic grows towards the optimum estimate much more smoothly than the IPDB heuristic, because IPDB can only increase or take the next variable into its pattern database once it is allowed to use much more states. Okay, so what am I working on? currently. One refinement that we did was not to look just for one optimal solution, but to check all optimal solutions in a single iteration, because we would have to otherwise refine them anyways in the next iteration. And this has improved speed up quite a bit. But the most important change was making the abstractions additive and using a set of them for search. And the paper about this will be presented at AAAI's late-breaking paper track this year. And this actually improves coverage quite a lot. So we see the three compared heuristics here again, merge and shrink and IPV. And previously, as you've seen, we were worse than the two best approaches, but with the additive abstractions, we can be better than all three of them. Something we still have to work on is how to select a flaw. As in the example you've seen, there were two different flaws that we could have taken, and it's not really clear which one would yield a faster estimate, a higher estimate faster. Also, we would like to find a better termination criterion for the refinement loop instead of just using a fixed timeout. Okay, so wrapping up, we have seen how cigar can be used for classical planning, and we've seen that it can yield a new admissible heuristic that yields robust performance in practice. Thank you very much.